Welcome back to The Explainer. Look, today we are diving straight into the absolute bleeding edge of theoretical physics, and we're tackling a mind-bending question. What if all that quantum weirdness we've been scratching our heads over for a century is, well, literally just a computational illusion? Get ready because we're about to build a completely new framework for how you view reality itself. I want to kick things off with this massive, almost absurd-sounding question. What if the infinite parallel universes you hear so much about in pop science aren't actually out there in the void? What if instead they're just an epistemic illusion, like a literal mathematical rounding error caused by our own finite processing power as observers? Sounds wild, right? But the evidence we're looking at today is incredibly compelling.
Okay, let's really dive into this. Mainstream physics is actually starting to admit a profound truth here. Space and time, they're increasingly being viewed as pedagogical tools, basically a convenience grid for us to describe things, not the fundamental bedrock of reality. I mean, we've assumed for over a century that the universe is this objective stage of 4D spacetime, but the math is straight up telling us something completely different.
So here is our roadmap for today. We'll move step by step through the end of spacetime, the many worlds trap, the finite observer limit, the deterministic substrate, and finally, the space-time illusion. All right, kicking things off with Section 1, the end of spacetime, establishing the stakes.
For decades, physics has been hitting a massive brick wall trying to quantize gravity. General relativity gives us this beautifully smooth, flexible canvas, right? But quantum mechanics demands discrete, jumping, quantized chunks of energy. And when these two clash, say inside a black hole, the math just completely breaks down. Our sources point out that our fatal mistake might be assuming space-time is an objective, unchanging background. Cutting-edge theorists are now realizing, hey, we shouldn't be trying to quantize spatial locations at all. We should only be quantizing the fields.
Moving right along to Section 2, the many worlds trap, specifically looking at Sean Carroll's multiverse.
So in the many worlds view, you take the foundational math of quantum mechanics, the Schrödinger equation, and you take it completely literally. There's no magical collapse when you look at a particle, no. Instead, every single time a quantum possibility occurs, the wave function of the entire universe literally splits. It creates an entirely new, physically existing, non-interacting branch of reality. And this all happens through decoherence, where a quantum state gets entangled with its environment, basically sealing off that new universe forever.
Look at the staggering contrast here. We go from the classical view, a single, neat Newtonian reality where things collapse into one definite outcome, to the many worlds view, an unimaginably vast, ever-splitting multiverse where every possible outcome, no matter how ridiculously tiny, is physically realized somewhere in Hilbert space. Now, it's an incredibly elegant mathematical solution, for sure, but it asks us to accept an absolute infinity of unobservable universes. Which brings us to Section 3, the finite observer limit. Time to pull the rug up. Now, here's the absolute crucial point. In this framework, an observer is not human consciousness. It isn't some guy in a lab coat making measurements. According to the system identification algorithm we're pulling from the sources, an observer is simply a finite informational agent. It's strictly restricted by its own computational memory limit, which is formally called its Shannon Information Capacity, or COBS. Think of it exactly like a hard drive that can only hold so much data on its outer boundary, its Markov blanket, before it is just completely maxed out. Now contrast that tiny finite hard drive with this absolutely staggering number, 10 to the power of 122. This represents the estimated dimensions of Hilbert space for our observable universe. We are talking about an overwhelming, practically infinite amount of continuous, perfectly precise math. Our finite hardware, our COBS limit, has to somehow process an environment that is infinitely more complex than we are. So, what actually happens when a finite observer tries to process infinite complexity? Well, the sources call it the wood chipper effect. First, the observer ingests this immense, continuous quantum data. Second, it instantly hits its finite memory limit. It starts acting like what computer science calls an FPU gambler, a floating point unit just forced to make hardware approximations. Third, to cope with the overload, it executes a mathematical rounding error, literally chopping off and dropping tiny trailing fractions. And finally, fourth, this irreversible loss of data accumulates as permanent observer debt. Because of this massive network complexity, a finite observer is literally forced to compress and permanently scramble the exact data provenance. The source material uses this brilliant metaphor. It's like a blended smoothie. You know exactly what fruits went into the blender, but because of your computational limits, you permanently lose the ability to reverse engineer those exact ingredients once it's mixed. The original data is just entirely scrambled.
All right, moving to Section 4, the deterministic substrate, exploring Gerard Tufte's reality.
To really grasp Kuff's model, we have to partition reality. On one hand, you have fast variables. These are microscopic, deeply hidden, and perfectly deterministic. They operate like a vast cellular automaton, with absolutely zero randomness, none. But because of our finite limits, our observer debt forces us to average them out. So what we actually see are the slow variables. These are macroscopic, probabilistic, and fuzzy. The big takeaway here? Quantum weirdness isn't the fundamental truth of the universe. It's literally just the blurry artifact of our slow, limited perception.
This completely changes the game. It means the famous quantum collapse, the idea of a particle magically choosing a location the second you look at it, it isn't a physical jump at all. It isn't a universe suddenly splitting into too many worlds either. It is purely an epistemic update. It is simply an update in our localized knowledge using Bayes' rule. The universe didn't physically change. Your ignorance simply decreased.
And that brings us to our final section, Section 5, the space-time illusion, the grand conclusion. Under the finite observer theory, the universe is a strictly static, n-dimensional relational network. Think of it as existing in a timeless hyperequilibrium. It doesn't compute, it doesn't evolve. What we actually experience as a 4D continuous spacetime is just a lossy, holographic projection created by our own finite memory limits. Macroscopic time? That's just our subjective illusion as we drag our awareness across a static gradient. And gravity? Gravity is literally just invariant entropic residue. It's a geometric artifact of our dimensional partial trace, honestly much like heat radiating off a working computer processor. Therefore, one of the absolute greatest mysteries in all of physics, quantum entanglement, isn't spooky action at a distance after all. It is strictly what this theory calls topological aliasing. When two particles seem to magically communicate instantly across the universe, it's just our continuous macroscopic map failing to properly render the underlying discrete, static network. The particles were never actually separated in the foundational geometry. Our limited 4D map just rendered them poorly. So just look at the stark contrast between these two frameworks. The many worlds interpretation demands that we believe in infinite, physically real universes branching out endlessly on a space-time canvas. But the finite observer theory, it brings it all back home. It proposes just one static, deterministic network. Superposition isn't some wild physical reality. It's literally our epistemic ignorance being mathematically rounded off. And space-time itself is just a projected holographic illusion born from our own limits. Which is why I want to leave you with this final, profoundly deep thought to ponder today. What if the mind-bending weirdness of the universe isn't actually out there in the stars? What if the multiverse, the quantum fuzziness, and the very flow of time itself are actually just the architecture of our own finite limitations reflecting right back at us? Thank you so much for joining me on this explainer. Keep questioning the systems around you, and I will catch you next time.